We've shared with you the ideal gas law, how it was developed, what experiments led to it, what does the math look like, what does it look like conceptually. Well, one thing we can do is we can use the ideal gas law to do some applications. The first one that we do is molecular weight. And it is from the ideal gas law. PV is equal to nRT, and N is grams over molecular weight. So when I substitute that into the equation, I get the following, and then I will solve for molecular weight. So how are we going to talk about this? Well, we're going to just substitute in. I'm going to say molecular weight is equal to grams RT divided by P times V. And I'm going to use the information I've been given. 0.109 grams, my universal gas constant, 0.0821 liter atmosphere per mole Kelvin. My temperature, I have to add 273, it'll be 373 Kelvin. Sitting on the bottom, I do just what I did in the earlier problem. 750 torr times 1 atmosphere is 760 torr. And my pressure, I hope I can take the liberty of making that 0.112 liters. Now, it did not take me long to write all that down. That's what we mean by practice. When you'll be taking your midterm exam, if you can come up with the right equation, put in the information you need, it takes about 6 seconds to type everything into your calculator. And you also have it all written down to double check your answer. So this is an example where we were given information and we could use the ideal gas law to find molecular weight. We can also use the ideal gas law to find density. So you know that PV is equal to N over RT. You know that N is equal to grams over molecular weight. So when you're looking at this equation that has the substitution, what you want to do is put it in terms of grams per volume, which is the density. Now, I never memorize the equation. I always derive it. But remember, you can have a little sheet of paper with your equations on it based on how things are going this semester. So here we go. Density is equal to P times molecular weight divided by RT. My pressure, I'm going to put in just like I have been. 750 torr, 1 atmosphere is 760 torr. My molecular weight, oh, what could it be for carbon tetrachloride? It turns out to be 154 grams per mole. Now, if I was giving this exam, I would give you the molecular weight because I'm testing to see can you find a density. Sitting on the bottom is my R, 0.0821 liter atmosphere per mole Kelvin. And I multiply that by 273, we have 398 Kelvin. When you crunch your numbers through, 4.43 grams per liter. So you see the ideal gas law can be used to find both a molecular weight and a density. We used to have a lab where you actually did find the molecular weight of a gas. A little bit more. You can use these gas volumes to do some stoichiometric calculations. Yes, the things that you left behind and hoped would never see again. I do 3 specific problems because each of them shows you something, all right? This first one says zinc sulfide reacts with oxygen to make zinc oxide and sulfur dioxide. We want to produce 0.50 liters of SO2. So we want to know the volume of oxygen gas that would be required. So I'm going to do a relationship. I'm going to put my volume of SO2 on the bottom. I'm going to put my volume of O2 on the top. And both of those are measured in terms of liters. Notice 3 is the stoichiometric coefficient for oxygen. 2 is the stoichiometric coefficient for SO2. That gives me 0.75 liters of oxygen gas. That is how simple this problem is. But again, I needed to show you that you don't always have to have moles. You can just use volumes and come up with your desired answer. The second one, it says what volume of nitrogen gas would be formed in a reaction of 0.86 grams of nitrogen oxide at STP. So how are we going to solve this one? This one also has something you might not expect. That's why we're doing it in class. 0.86 grams of NO. Normally, I'm hoping you're saying, oh, I simply better turn them into moles of NO. And that's 30 grams of NO for every mole of NO. Now we're going to use the stoichiometric ratio. We're looking for moles of N2. We have moles of NO, and we look at our equation, and we have a number 1 and a number 2. Now, the reason we're doing this is we're saying this is an ideal gas. If we have an ideal gas, 22.4 liters for every mole, and we will come up with 0.232 liters of nitrogen gas. Again, practice, because no one is born knowing how to do these problems. I'm hoping that the first part of this problem, the setup, you breezed through. That's what we taught you in chapter 3. What we're teaching you now in chapter 9, or excuse me, 10, is how this works in terms of gases. One more, and this is, notice it says in red, a multi-step problem. First, you're going to find the moles of NO2. Then you're going to use that to find the moles of HNO3. Why did I choose NO2 first? Well, they tell you 450 liters at 5 atmospheres and 295 K. They have given you the volume, the pressure, and the temperature. That means you can find the moles of NO2. Then you can use stoichiometry to find the moles of HNO3. And again, this is the kind of question you'll see on a midterm, where you have to do more than one step. So what I have here is, I'll just write it out. I'll say my moles of NO2 are 5.00 atm times 450 liters divided by 0.0821 liter atmosphere per mole Kelvin times 295 K. What I should have said is N is equal to PV over RT, but no, I jumped in and started putting in the numbers. That says 92.9 moles of NO2. Now, you're given the equation above. You can see that 3 moles of NO2 are going to give you 2 moles of HNO3. I'm going to continue the calculation on the spot. I guess I have to do it here. 92.9 moles of NO2 times 2 moles of HNO3 for every 3 moles of NO2 will give you 61.9 moles of HNO3. Now, in the old days, when one could look at their questions on an exam back and forth, I would often give a question like this. It is a little bit more involved. Realize, rather than just given these things, you could have been asked for grams. Be versatile. Understand what's going on the next blank spot, okay? Oh, there is no. So what's on this last slide? Well, we got to have a little bit of fun. When you have CO2, which is dry ice, which there is a shortage of in order to ship the COVID vaccines, they're only making it on the East Coast. When the dry ice goes from the solid to the gas phase, essentially, when we look at the cloud, it is not CO2 gas. It is actually water vapor condensing in the air by cooling. Air contains water vapor. It's what makes your hair frizz. So essentially, I had to end this on a high note. As you work these examples, do some more. Line these up next to something you're trying to do. Realize it's up to you to now set up the problem. It is hard, but it will get easier the more you practice.